So far we have described the two ports using the relationships between the port currents and port voltages. They turn out to be linear combinations. In some contexts, it is useful to have a circuit representation for the same relationships. That is what we are going to look at in this lesson. Okay. So, let us say we have a 2 port and we choose to use y parameters. Okay. That says that I1 is y11 V1 plus y12 V2 and I2 is y21 V1 plus y22 V2. It would be useful to have an equivalent circuit which realizes these equations. Okay. This is analogous to, let us say you are given a box, okay, with linear elements inside, then you could provide the relationships algebraically. V1 equals I1 times R equivalent, or equivalently you can say, let us say this is terminal A and terminal B. You could say that between A and B you have this equivalent resistance. You could show this picture instead. What we are going to do is similar to this. Instead of showing the equations, we will show the picture. Okay. So, for each of these terms there will be a corresponding element. So, let us say this is port 1, we have V1 across it. The current flowing into port 1 is a sum of two parts, y11 times V1 plus y12 times V2. First let us look at this y11 times V1. Okay. So, it is flowing into port 1 and it is also related to the voltage between the same two terminals 1 and 1 prime. Okay. Clearly, if we had just this part, let us say I1 equals y11 times V1, that would correspond to a conductance or a resistance. Okay. So, if I have a conductance whose value is y11, it will draw a current which is y11 times V1, because it is placed across V1. Okay. Across this conductance we have a voltage V1. Now, we have the second part y12 times V2. So, this is 2 and 2 prime and V2 is over there. So, there is a current drawn in port 1 in response to a voltage in port 2. So, this is clearly a dependent source or a voltage controlled current source whose value is given by y12 V2. Okay. Similarly, if you look at the second equation, we have I2 equals y22 times V2, that is one part of it, and that is the relationship between the voltage on port 2 and the current in port 2. So, it is represented by a conductance whose value is y22, and this last part y21 times V1 is represented by a control source like this. It is I2. So, it is the current drawn from port 2 and it is proportional to V1, that is voltage elsewhere in the circuit. So, it is modeled by a voltage controlled current source and its value is y21 V1. Okay. So, this picture with these 4 elements, 2 conductances and 2 control sources, says exactly the same thing as what this equation is saying. Sometimes when you are analyzing circuits, it is useful to put down this picture instead of the 2 port. Okay. And sometimes some of these relationships become very obvious when you put down the picture instead of manipulating equations. Okay. Now, a similar thing exists for all 4 types of parameters, that is what we are going to look at. Okay. Now, we consider the Z parameter representation of the 2 port, which gives you V 1 and V 2 as linear combinations of I 1 and I 2. Okay. So, again let us say this is port 1 and a current I 1 flows into that port and we have V 1 across it. We see that V 1 is a sum of 2 quantities. So, that means that there should be some 2 voltage drops in series to realize this sum. Okay. Now, the first one is Z 11 times I 1, that is a voltage drop which is proportional to the current flowing through the port. So, if I have a resistance whose value is Z 11, the voltage across that will be Z 11 times I 1, because I 1 is flowing through Z 11. The second part of it, Z 12 times I 2, it depends on the current elsewhere in the circuit, that is in port 2. Okay. So, we have the second port V 2 across it and I 2 through it. So, in series with this resistance of value Z 11, we will have Z 12 I 2. Okay. And similarly, for the second equation, we have a series combination of 2 voltage drops, one which is Z 21 times I 1, because it depends on the current elsewhere in the circuit. We have a current controlled voltage source whose value is Z 21 times I 1, and in series with that we have a resistance Z 22, because I 2 is flowing through Z 22, it creates a voltage drop Z 22 I 2. Okay. So, again this equivalent circuit enforces the same relationships between the port voltages and port currents as do these set of equations. Okay. Sometimes instead of using these equations, it is useful to write this picture and then maybe add in whatever else comes from the rest of the circuit and proceed with your calculations. Okay. Now, we will look at H parameter representation of the 2 port. Here again we have 2 equations. V 1 is the sum of 2 quantities. Since a voltage is the sum of 2 quantities, we can think of each of these as individual voltage drops which appear in series to form V 1. And in the second equation, I 2, a current is sum of 2 quantities. Since these 2 currents sum up to give this, we can think of these 2 as parallel branch currents which add up to give I 2. Okay. So, as you expect from the name hybrid parameters, the equivalent circuit will also be a hybrid. On one side it will have series branches and on the other side parallel branches. Okay. So, let us say this is port 1 with V 1 across it and I 1 through it, and this is port 2 with V 2 across it and I 2 through it. Okay. So, V 1 is a sum of these 2 drops. Okay. So, we have a resistance whose value is H 11 and we have a control source. This V 1 depends on V 2. So, this is a voltage controlled voltage source whose proportionality constant is H 12 or whose value is H 12 times V 2. Okay. Now, for the second equation, we need parallel branches because we need to add currents. So, we have I 2 H 22 V 2. So, I is proportional to V. So, this is a conductance and the conductance is H 22 or the resistance value is 1 by H 22. Okay. And finally, we have a current controlled current source because I 1 is a current, the resultant I 2 is also a current. So, this term is created using a current controlled current source. Okay. And the gain of the current controlled current source is H 21. So, this is what we have. Okay. On port 1 we have series branches, on port 2 parallel branches. Okay. Finally, we will look at G parameters. Again, we have two equations, each with sum of two terms. The first equation results in a current, which is a sum of two currents. So, we need parallel branches to implement this. The second equation is a voltage, which is a sum of two other voltages. So, we need a series combination to implement that one. Okay. So, port 1 we have the voltage V 1 and the current I 1, and port 2 with voltage V 2 and current I 2. Okay. So, the first one is a current. So, we have sum of two branches G 11 V 1, that represents a conductance of G 11 or a resistance of 1 by G 11. The second one gives the dependence of I 1 on I 2. So, this is a current controlled current source. Whose gain is G 12 or whose value is G 12 times I 2. Now, on the other side, on the second port, we have the voltage as a sum of two other voltages. V 2 equals G 22 I 2, voltage proportional to current, which is obtained using a resistor whose value is G 22, and in series with this is a voltage controlled voltage source. Okay. V 2 equals G 21 V 1. So, it is a voltage controlled voltage source of gain G 21. Okay. So, this is the equivalent circuit for the G parameter 2 port. Okay. So, like I said, any network can be represented by any set of parameters. Of course, sometimes some of these parameters are infinite valued, in which case you do not use them, but in general you could use any one of them. Similarly, you could use any one of these equivalent circuits. Now, again, which one you choose is based on convenience. Okay. Exactly like either choosing to calculate with resistances or conductances. Okay. Here we do have more choices because we have two ports, more variables and so on. Okay.